Okay, I'm recording. I'm going to talk about complex numbers under multiplication. And I'm going to show that this is a group, or at least the complex numbers without zero. So we're considering the set of complex numbers without zero, because of course zero doesn't have an inverse. Okay, well let's just define complex multiplication. A plus bi times c plus di, you'll have seen this before, equals AC minus BD, that's the real component, plus I times AD, that's that term, times that term, plus BC. So we've got two complex numbers there, this one, and the product is, that's the real component, this number here, with this real component here and this pure imaginary component. Okay, well that's great. Let's just verify that they're a group. So first of all, is complex multiplication closed? Well, yes it is, because if you get a complex number and multiply it by another complex number, you've got another complex number here. So yes, it's closed. Is there an identity? Well, yes, of course there is. It's 1 plus 0 times I, perfectly respectable complex number. Let's just verify that. A plus bi is 1 plus 0i. You just go through the notions, and it's a plus bi, so that works. And it's also a right identity as well. Also a left identity, I'm sorry. Bi equals a plus bi, simply by going through this definition here. Inverse. Well, yes, there is. A plus bi to the power minus 1 equals a minus bi over a squared plus b squared. Let's just check that. A plus bi times its inverse, which is a minus bi, over a squared plus b squared, equals, well, it's over a squared plus b squared, and here the real component is a squared plus b squared, because it's a times a. You notice it's plus b squared because it's negative, but I squared is equal to minus 1, of course. What's the imaginary component? Well, that's worth working out in excruciating detail. Just rewrite that a bit more neatly. That's a times minus b, so that's minus ab for that one, and the term this one times this one is this plus b times a. So of course this is equal to 0 here, so the numerator has got no complex part, and so it's just a squared plus b squared over the denominator, a squared plus b squared equals 1. I guess plus 0i if you want to put that in there as well. So that works out, and we've got a nice inverse there, which we knew anyway from complex analysis. The third one is associativity. Just remind ourselves what that means. X, Y, Z equals X, Y, Z. Well, we better verify that. I'm going to say X equals A plus BI, Y equals C plus DI, and Z equals A, B, C, D, E plus FI, where A, B, C, D, E, F are real. Okay, so there's the left-hand side, and there's the right-hand side. We better evaluate these guys. What's the left-hand side? Well, it's A plus BI, C plus DI in brackets times E plus FI. Well, let's just do that. Let's work out the real component of this one here. It's going to be AC minus BD plus I times AD plus BC times E plus FI. So you see, all I'm doing is going through the motions of expanding out this this term here, with x, y and z as specified here. Okay, well we better work out what that is. What's the real component? Well, it's AC minus BD times E minus, because I times I is minus 1, AD plus BC times F, because we're doing the imaginary times the imaginary component, plus I times what? Well, it's AC minus BD times F plus this term times that term times this one, AD plus BC times E. Well, we better simplify that. We've got ACE minus BDE, that term and this term, minus ADF minus BCF plus I into ACF minus BDF plus ADE plus BCE. There it is. Oh, I've opened a round one and closed the curly one. Alright, so that's my left hand side. I'll just pinch that in a little bit. That's my left hand side, which is rather a complicated expression, but we'll come back to it. Actually, I'll do the right hand side in parallel. So here the right hand side is going to be A plus BI, that's my x, times y times z. So I'll put some brackets here, and then yz. So ABC plus DI E plus FI. So it's A plus BI times CE minus DF, that's the real component, plus I DE plus CF, that's the imaginary component. Okay, so let's just have a look at this. We'll do the real component, A times CE minus DF minus B times DE plus CF plus imaginary component, it's B times CE minus DF which one have we done? We've done the B times that. We need to do plus A times this term here, DE plus CF. So I'll just do a little bit of tidying up there. That's ACE minus ADF minus BDE, this term here, minus BCF, plus I times BCE minus minus BDF plus ADE plus ACF. And now, hopefully, if we've got everything right, we will see that everything cancels out in pairs. I'm going to use red for cancellation here. We've got ACE there, ACE there, BDE, minus BDE I should say, and then minus BDE, minus ADF, minus ADF, minus BCF, minus BCF, ACF in the imaginary component, ACF, minus BDF, minus BDF, plus ADE, plus ADE, haha, plus BC, plus BCE. So they all, each component on each side has a natural, has an equivalent term on the other side. So the operation is associative. I just want to make a couple of observations here. The first observation is that this was not at all obvious. Complex number multiplication, or complex multiplication being associative, is true, but extremely, well, I won't say tricky, but there's no way to do it other than just by expanding out your terms there. It's quite non-obvious. And the second thing, or the second observation, which I've sort of fudged, I haven't really been entirely honest about this, is that the associativity requires the associativity of real multiplication. I've just casually written down this term here, for example, as just ACE, without regards to the brackets, AC times E. I've just casually used the associativity of the reals there, which was a bit cheeky. I should have been a bit more explicit about that, but we all know that the real case, or the real multiplication, is associative anyway. So what I'm doing is assuming that, basically, and not having to worry about it. But it's worth observing. So, overall, we have got complex numbers without a zero, and complex numbers without a zero are a group, because the operation is closed, it's associative, it's got a neutral element, which is just 1, of course, and it's got an inverse, which is this formula here. And of course, this formula here requires that the number is not equal to 0. So, complex numbers under multiplication are a group. Complex numbers without 0, under multiplication at least, are a group. I'm going to stop there.